So, whenever we have unbalanced experiment, when this is very common, okay, you have different treatments, but number of samples in each treatment will be different, right. You cannot exactly conduct 100 experiments for each treatment, probably in one treatment you may only have 20 or 30 might have signed for the drug, others might have more people would have signed up for a different drug. So, you cannot always conduct a balanced experiment. Conducting experiment is the most difficult part, balanced experiment is even difficult. What do I mean by balanced? Each treatment has same number of samples. Remember, we have assumed all samples have, all treatments have n samples, small n samples, which need not be true. Okay. Each sample, each treatment may have different number of samples, that has to be accounted for, okay, and that is where we are accounting. So, now we will have unequal samples. So, the sum square total is obviously going to be different, where you see, okay, it is different for each different. So, I had NL, okay, it is different for different, the total N is different, and I have L equals to 1 to A. So, for each treatment it is going to be different, okay, I think yeah, that is what I am writing it out. So, now I have L is another index which determines the number of data points and number of samples in for each treatment. So, obviously my sum square treatment has to be changed, and this is what the sum square treatment is, where capital N is nothing but summation of all the data points, but for each treatment the number of samples is going to be varied. Which sigma squared? Sigma squared. Sigma squared is the same. There no relaxation, at least in ANOVA we do not have sigma squared different. As I said, then there you are not comparing apples against apples, right, you are comparing two different, altogether two different quantities, okay, make sense. So, this sum square total will vary, and you know, of course, conducting balanced experiment is useful, unbalanced experiments will have its own challenges, the degrees of freedom all of them will get slightly hurt, for each treatment it will be different, okay. And his question is very relevant, if the number of samples is too small, your estimate of sigma squared will get affected. If you have, say suppose you have 10 or 20 samples for each treatment, you calculate sigma squared, which is your MSE for each to be the same. Now, you have only 2 samples or 3 samples in one treatment and 40 samples in another, your estimate of treatment variance will be a problem, okay. So, it is important to keep the experiment balanced as much as possible. See, if it is insensitive to small departures from the assumption of equality if the sample sizes are equal. If the sample sizes are unequal, then estimate of variance becomes itself a problem, and therefore, all your underlying results will be at stake if you are too much unbalanced, okay. Remember, even in machine learning there is all these algorithms, there is a big catch, whenever you have skewed data, they call it again imbalance, class imbalance. Have you heard of this term called class imbalance? No. So, suppose I have 99% of the time you expect an industry to work properly, let us say a chemical industry. If any harm happens, what will anything goes wrong, what happens? Explosion, hazards. You expect the plant to happen, a chemical plant to give abnormality daily? No, right. So, 99% of the time it works normally, only 1% of the time or less than 1% of the time there will be issues, abnormality. Same with humans, do you expect 99% of the humans to have heart attacks daily? No, right, and that too a particular case, not at all. So what about even about you when you collect data from your watch or when you collect data from whatever, right, how much of it will be abnormal? Very, very less. But what is of interest to us? The interest is to catch when abnormality happens. So the amount of data that will be available to actually model your abnormality will be less. This is called class imbalance. You have a huge amount of data when things are working fine. When things are not working, you have very little data. And what is of interest to me? To capture when there is abnormality. Okay. That is why these kind of problems are tricky. At least with humans, there are so many humans there, so that you can learn from others. Okay. But if you look at a chemical plant, there are not many chemical plants which produce the same component, right. So if the plant is operating normal, I will have so much data. How many Bhopal accidents have happened? But can I, that is very little data, right. So with that data I should predict that there should not be one more Bhopal incident. How do I do that? This is called class imbalance data. Okay. So whenever imbalance is there, it will present with its own challenges. Your model accuracy will be 99% good. Why? Because 99% it is working fine. I mean the data is normal data. Your accuracy will be, suppose your model is 99% accurate. Do you think the model is good? Maybe 99% accurate because it is only predicting normal condition. Wherever 1% it has to predict, it will fail. Is it of any use? So all your measures of accuracy, everything changes when there is class imbalance, when there is imbalanced data. So therefore, it is very important when there is an imbalance, it has to be considered separately. Okay. A word of caution. Now how do I know that your ANOVA, whatever you did, the hypothesis, that is fine? This is a very important question. So far we haven't asked, but the first time we have developed a model here. How do I know that my ANOVA results are good? I have said statistically none of them is, statistically at least one is significant. Okay. Let us assume we have got and made it confidence interval, etc. But how do I know that even my methodology is right? We haven't asked this question earlier in hypothesis testing. How do I know that I have conducted a right hypothesis? What should I look for? Why do you think ANOVA is the best approach here? Has given you the best result, what you wanted. How do you support your claim? You understand my question? I have given you data, you conducted ANOVA and you said look, at least one of the treatment is significant, and you said considered whatever hypothesis testing and said this treatment is significant. Now I ask you a question, why should I believe you? Then we go back and ask about the assumptions we made in ANOVA. Is this assumptions valid? Is the data also stating the same thing, meaning I have assumed something about the experiment and I have conducted ANOVA, I have got the results, but now I want to know whether my assumptions in this process is right. So what is the important assumption which we made when we started the model for ANOVA? The underlying distribution is normal. Each population's underlying distribution is normal and its variances are equal. Okay. So that is one thing to be tested. If underlying distribution is normal, so what about your mean squared error? Mean squared error should be normal, right? Your mean squared error should be normal or Gaussian distribution. So the first thing to check for is residuals. Okay. So you talk about what I call this thing. Okay. So you have hardwood concentration and I have what is called as residuals. Any idea what is residual? What is the residual? Residual, literal meaning. Remaining. What is remaining? Abnormality. Remaining is what? Remaining is difference between something. What is the difference? What is the model we have? You have data, okay, that is the real observation. But what is the model's output? So remember, we had, what is this? This is y equals to yij equals to mu plus tau I plus epsilon ij, or this is mu I plus epsilon ij. What is the estimate of mu I? What is the estimate of mu I? What is the estimate of mu I from the data? Yi dot bar. And what did we assume? We assume this is normal mu comma sigma squared over n, which is normal mu comma MSE over okay, right? Yes or no? This is what we assumed. So now what is this? This should be Yij minus mu I, which is nothing but Yij minus Yi dot bar. So the difference is what? Remember, what is noise? What is noise? Sum square noise is what? Sum square error is what? Yij minus Yi dot bar the whole square. What is sum square treatment? Sum square treatment is Yi dot bar minus Yij the whole square. If you look at it, this is the first thing we derived. The first part is sum square treatment is Yi dot bar minus Y bar dot dot the whole square is the treatment part, and noise part is of Yi j minus Yi dot bar whole square. This is noise part, right. This is what first thing we did. So coming back, what is residual is the difference. So difference of what? Difference of the observation minus the estimated mean value, which is Yi dot bar. So I can compute what is known as the residuals for each row, that is for each treatment. Y1 dot bar is known to me, Y2 dot bar is known to me, Y3 dot bar is known to me. So I can compute the residuals. Now these residuals should be, how it should be distributed? Normally distributed, because my assumption is the underlying population is normal, mean square error is also normally distributed. So first thing to check for is normality plot. Normality plot of residual, which is Yij minus Yi dot bar. You understand now what is the residual? It is difference. It is difference between observation and estimate, right. What is the observation? Yij. What is the estimate? Estimate is mu I. The estimate of mu I is Yij, Yi dot bar, that is what. And the remaining is what? The residue, which is actually should be noise. What did we assume about epsilon ij? We assumed epsilon ij is what? Normal 0 comma sigma squared. Okay, when you do sample, it will become sigma squared over n, but the true assumption is about noise is what? 0 comma sigma squared. So this should also have residual should be normal first. So if your residual is normal, then you can say that, look, I made an assumption that the residual is normal, I did the experiments and it turns out that my residual is also normal. So I have a confidence in my approach, I have a confidence in my ANOVA approach, because whatever assumption I made, that assumption is getting validated using the data itself, because this is validation using data. Then what else assumption you have done? What else you have done? Normal all of them have almost equal variances. So then for each treatment I can plot the variance. Look at this, this is my plot of residuals for treatment 1, treatment 2, treatment 3, treatment 4, more or less same is what you should say. It is not like very rapidly very large. Okay. You can do a statistical test also, but at least from the plot you should be able to get a quick look whether the variances are equal or is it glaringly different. Okay. That is another assumption which we made, we could test it. Okay. What else we can do? I have actually put the residuals, no? These are residuals for each treatment, 5%, 10%, 15%. So this is the overall spread in the data. So what is variance? Square of the spread, that is all. Statistically, you look at the length of the bars, take for example 5% and 20%, are they very different? The spread is the overall thing, is the spread looking very different? 5% and 20%. I know 5 and 15 may look small, 15 is looking small, but 5 and 20 almost, right. So those are quick visuals to take and say is there something glaringly wrong or not. Okay. So this is where we say okay, I have confidence in my approach. Okay. That is what we should be doing. Clear?